on the board that and robots move in a way that if there is no wall, it moves in 0 seconds. If there is a wall, it moves in 1 second. And you want to make such field that all robots reach the final cell at the same time. And you need to count the number of such fields. So, okay, the other way to look at this problem is let robots move backwards, let them start from the finished cell and go to the first cell. So what you want to have is that you want, let's swap this. You want all the paths to all cells in the final row and the final column be the same, all distances be the same. Okay, let's use dynamic programming. So let's count the number of. Let's count this. So you add the cells to the field one by one. When you add the cell, you have options. You can put one of these two walls or both of them, or not put. So at most 4 options. Maybe some of the walls are already there, so you are told that there is no wall. So at most 4 options, at least one. When you add the cell. And what do we keep track of? The first idea, we just keep track of the shortest path to each of these. So it's m times n, m plus 1 cells. So we say that the shortest path to this cell, to this cell, to this cell is this and this. M is at most 5, if I remember correctly. Or 6, something like that. Let me check. F. Yes, M it's at most 5. So m plus 1 is at most 6. The next thing to optimize here is that actually the only thing that you are interested in is that all these distances in the end are equal. You don't need to make them all some particular value. So you don't care about exact values, but you only care about differences between them. So you can say that you store here's some value, distance to this cell that you don't care about, some value it has, and you only have deltas, delta 1, delta 2, 3, and so on, differences between this cell and the first cell or the previous cell, whatever. So this gives you some set of possible states. So your state is how many complete columns you have processed, how many rows in the last column you have processed, and what is the pattern of these deltas. And you make like a map from this state to int the number of ways to reach this state. And you make dynamic programming, or like maybe like BFS or something. You take the state, you add the new. Well, actually, you don't need to remember this one, I think. It doesn't influence anymore. So, actually, M. Only M. You don't need this one. You cannot go by diagonal. So, you just check what is the shortest path to this cell. You come either from here or from here. So, you choose which of them is shorter, for this case, to get a new pattern of distances. And you store it in state. So the number of reachable states is not very big. I think it's something like 300,000. Well, that's the way to solve this problem. Is it new to you to do such dynamic programming? Do you want me to give more details later on such problems? No? Yes? Okay, then I didn't prepare today, but I probably will give you one of the 2 other days I will have, or I'll ask Adam to give more weird dynamic programming problems. Okay. Okay, so please try to upsolve it. You will have a sponsor day today, so after you finish up with our good sponsors, you will have some time to upsolve. Okay, so now the problem G-H-I over K, problem J. Problem J was very easy, but you must have an insight to solve it. So the problem is you have some connected part of the board composed of unit squares, and you do the following. You split every square to 2 parts. So let's split only squares of our field, like this. And now you have to find a Hamiltonian cycle at this part of the board. Let's do the following. Let's run DFS on the initial not duplicated figure. So on the initial figure, before we cut each cell into 4 pieces, let's make DFS and let's create the following. Let's create a DFS tree by connecting centers of the square. So let's go start DFS from here, go here, go here, go here, return, go here, return, go here, return. So if you look at the picture after this, you see that if you keep the walls and add these DFS edges that you move along, at the walls, what remains is exactly the kind of Hamiltonian path. So if you walk along this road, not exactly, if you walk along this road, if you use like a labyrinth exit rule, go with the left hand on this wall. So you take and walk along this GFS tree by always touching it with your left hand. So if you do so, if our girl from this problem does so, then she visits every cell exactly once, which is required. So that's it. The other way to do it, yes, I forgot one thing. If you go between two cells by DFS, you draw a wall. If you don't go, you draw a wall between them like this. Yes. If you do like this, you can also, the other way to look at this, you get this particular path also. Just build these walls. Okay, now finally, before we move on to our today's theory classes, we have the final problem to discuss, K. Problem K is geometry. So almost nobody tried it. There's one team that had it. It's Kolopsida team, which we already know. Yeah, great job. And let's see how to solve problem K. The problem is we have two polygons. We have two polygons, and we must put one of them into the other one, so that after that, so we have two polygons, like square, the big one and the small one. You have to put small one inside the big one, and after that the following takes place. A circular car runs around the smaller polygon, and you want to put it in such a way that the size of the car that can run around it is as big as possible, the biggest possible car. So what is the possible solution to this? First thing that we do in such problems always is to do binary search. So we binary search on the size of the car. The next thing we would like to do is to reduce the problem to a point, not to a circle. So what we can do, in this case, we could either shrink the bigger polygon or expand the smaller polygon. Which is better? Actually, in this problem, to shrink is better, because if you expand it by the distance of the diameter of our car, then, okay, the sides go away this distance. No. But we also get these rounded pieces, and it's not very pleasant to work with them. But if we shrink the bigger one, well, okay, it shrinks. So, and now we want to put the smaller one into the bigger one, so that it completely fits. It completely fits if we fit all of its vertices, because both polygons are convex. Okay, so let's see what does it mean to put the vertex in the polygon. So, okay, let's say we have a polygon. Its interior can be said to be the intersection of half planes. So you go along the edge of the polygon and you say the vertices, the points of the plane on my right are inside. So the points that satisfy all these conditions are inside this polygon. So take this line. So it's like, take this, for example, is equation a times x plus b times y is c. So the points on one side and on the other side are different by the sign of this. Let's say plus c is 0. By the sign of this part. So 0 is on the line, positive is on one side, negative is on the other side. So if you create this equation in the same algorithm for all adjacent vertices of the polygon, you will get right side and left side as walking around the polygon in a consistent way. So either they will all be positive or they will all be negative. So let's say that all of them are positive. So we have for each such point, so that a times x plus b times y plus c must be greater or equal to 0. So that's the point inside this polygon. But we actually don't want to put the point inside the polygon. We want to put the polygon inside the polygon. Well, okay. Let's check now the smaller polygon. And say that this is its origin point, so it's 0, 0. Actually, it doesn't really matter. Say it's x1, y1. So we want to shift them all by the same value. Shift this one here, yeah? so that all these points satisfy these equations. So say we shift it by x, y. So for each vertex of this smaller polygon xi, yi, we have put it here and get a times x plus xi plus b times y plus yi plus c is greater or equal than 0. So xi and yi are actually the coordinates of the vertices of smaller polygon, and they are constants. We only need to find x and y. So we expand this and get the following: a times x plus b times y plus a times xi plus b times yi plus c is greater or equal to 0. So we actually get the new requirement for the point x, y, that is inside some half plane. But we have now moved this half plane this distance. Actually, we will, for all vertices of this polygon, we will get this equation, and all half planes of this bigger polygon, we will get this equation. And not equation, inequality, yeah? This inequality. And we will need to satisfy them all. Well, the ones with the same a and b, so the ones for the same bigger part of the same side of the bigger polygon, they are all similar, and there is the one among them that is hardest to satisfy with the smallest this coefficient, because we need to plus this to be greater or equal to 0. So this value must be the smallest to be the hardest to satisfy. So we can actually keep only one of the, we have n sides here, m sides here, we have n times m such equations, but we, for the purpose of half-plane intersection, we can only keep the one for each of the sides of bigger polygons. And then when we have them, we want to find if there is a point inside of all these half-planes. There are several ways to do this. Because the constraints are rather small, there are at most 100 sides here. You can use, for example, the following way. You start with some very, very big space square, so with coordinates infinity, infinity, not actual infinity, but very big infinity, and so on. And you get these half-planes one after another. It comes, so here's the line, and cuts away the part of our polygon. So we get, in a general moment of time, we have some polygon, and if it is all inside the half plane, okay, we just drop it. If it is all outside of half plane, then we say no solution. And if it crosses here, then we walk around, find intersection points, cut away the part that is outside, get a new polygon. It's 100 half planes only, so we can make it as small as we are, or as slow as we can, just some way find it. So we only need Boolean value. We don't need the resulting shape. Actually, we only need Boolean value because I have a binary search, and therefore, if either we get a good result or we get a bad result for this binary search, so we go up or down. So that's it. That's the problem. Well, it is not very difficult, but it's pure geometry, yes, so you have to make all geometry things intersect lines, intersect polygon with a line, so all such things. How did you use this way to solve it? Yeah, okay. Okay, so that's about yesterday's problems. Any questions or comments? No questions, no comments. Okay, then we're okay on schedule today. It's okay, we have plenty of time. So while you are still fresh and not tired, let's start with theory, and we'll make a break a little bit later then. Just 40 minutes into the class. So okay, let's see. The lecture today will be data structures. And we will start with a part that is about persistent data structures. So what is the idea behind persistent data structures? Persistent data structures are data structures that keep their previous revisions. So when you modify your data structure, you can still access previous revisions of your data structure. There are actually 4 levels of persistence. In theory, these levels are partial persistence, full persistence, confluential persistence, and fully functional data, purely functional data structure. So partial persistence means that you can have read access to previous revision of your data structure. So when you have a data structure, you can access its previous revisions. Full persistence means that you can not only make a read access to your previous revisions of your data structure, but also write access to that. So in partial revision, partially persistent data structure, you start with some revision, you go on, and you can read previous revisions, but you cannot fork from them. In fully persistent data structure, you start with something, can go and see, and also create new revisions of your previous revisions. Confluentially persistent data structures have the property that you can combine different revisions of the same data structure in the same operation. So if there is an operation that takes several instances of our data structure, then you can combine them in one operation. For example, if you have a Cartesian tree, a tree, then you can merge trees. Yeah. So if you merge different revisions of the same tree, and if you implement a tree in such a way that you can do it, then it's confluentially persistent implementation. And finally, the purely functional implementation. Purely functional is actually not a capability but implementation detail. If you have classes on functional programming languages in your universities, you probably know that in functional languages you cannot use variables in the way you do it in imperative languages. You cannot say assign variables, run cycles for some variables, and so on. You once you assign some value, you must keep it there. So you use recursion or some lambda expressions or something like that to work with values, but you do not simply assign values. So purely functional data structures have a property that you can only assign values to variables once. So a variable can be undefined yet, or it can be assigned some value and you cannot change the value. So that works. That gives you actually a persistence in any possible way, because if you cannot change the value of any variable, you cannot intentionally destroy the revision of your data structure. It will be there anyway. So you can access it, you can fork from it again the same way you did it initially, and so on. So to get some sense of persistent data structures, let's start with two most basic ones. The very simplest one is a stack. Let's make persistent stack. So what is a stack? You have a stack, yeah? So you can push from this end and pop from the same end. So let's implement persistent stack. It will be very easy. So what is a persistent stack push operation? So you have, what is a stack? Let's keep stack as a list, linked list, one directional. For each vertex, we store a pointer to the next one, which is under it in a stack. So when you push something onto a stack, you create a new vertex and say that its next vertex is the top of the stack before this push. And when you pop something from the stack, you just move along this next pointer to get the new top value from your stack. You just don't free your memory, so you still have access to all the previous revisions. So in this sense, push to the stack S and the value X, get something like return, you stack with let's say asterisk, you stack with the value X and next as S, yeah? And pop from the stack S, we return the value on the top of S, and we return the new revision, which is stack next. So it's very easy. How would a persistent stack look like in the memory of our program? That would be something like the tree. So when you say you have initially an empty stack, when you push some value, so say we have push 2 to revision 0. We now only have revision 0. Then we would have a 2 that has next as nothing, and that's revision 1. That's revision 0. Say now we have push 3 to revision 0. Well, okay, then we have a new vertex 3 that has next link to this empty stack. Then we say we push 1 to revision 1. Then we have a new vertex like 1 that is now revision 3. So we then push again something 5 to revision 1. We get a new vertex containing 5. Oh my, revision 4. Then we say we pop from revision 3. We return this value 1, and our new revision 5 is again this position. So that's like a tree. It's very easy, it works, okay. So the more common to use to implement some persistent data structure is a segment tree. Let's make a persistent segment tree. Well, actually, when you usually code a segment tree, you store, you pack it into an array like binary heap. So you store left vertex in 2 times I plus 1 for a vertex I, and the right sum in 2 times I plus 2, something like that. When you are working with, when we will now be working with persistent segment tree, we will not be able to do this because we cannot, the structure of a tree will move around. So we need to make something more similar to a tree. We explicitly store pointer to our left child and to our right child because they will change partially. So our node will now have left and right pointer, and all the other things that a typical segment tree has. Whatever you need, you can make some delayed operations, pushes, or something else. So you store some value for whatever operation you need and whatever else you want. So let's see. Let's take, for example, a minimum operation and 4 elements. So we have like this initial segment tree, and say we have 3, 1, 2, 4. So it has 1 to 1. Now when we change the value in our segment string, when we are working with persistent data structures, the simplest way to work with them is to use the purely functional approach. We don't modify values in existing vertices, but we replace values, but we create new vertices and use values from parts of our existing structure and create new values. So for example, say that we want to change this one value to, say, 5. What we would do, we would go down, we have found this vertex, now we need to change it. We cannot assign the new value in persistent data structures. We need to create the new one. Okay, we create the new one, it's 5. So, okay, we return up. Here, again, we cannot change, we now need to make, first we have a new right sum, which is 5. And second thing is that we must replace the value because now the minimum of 3 and 5 is 3, not as previously it was 1. So we again cannot change the value. We create the new value. It will be 3, and its left sum is same as previously it was, that value of 3. And the new value and the right sum and the new one. So now, again, going to the root, we need to create the new root. It has new left sum, this one, and the right sum is the same as previously. And the minimum of 2 and 3 is 2. So actually, as you can see now, if we look at this persistent range, persistent segments tree, range minimum query tree, from this point of view, you see the initial revision of our tree. that has 3, 1, 2, 4 and corresponding segments minimum. If we say that this is the root of a tree, and we look at this, then we see 3, 5, 2, 4 values and corresponding minimum. And this revision doesn't actually know anything that there was some other revision. It has just looks as if it were the only one. So working on read requests on segments tree don't change. Actually, that's not exactly true, because, as I think you know, sometimes when we make group operations on segments tree, for example, changing values on some segment or adding values to some segment, these operations have read operations can modify a segment's tree because they make push operations. Yeah? You can make this on persistent segments tree as well, but you must keep track that read operations modify segments tree, so you will have to create a new revision on that. And the second problem is that we will now see on 2 examples is that amortized analysis doesn't work for persistent data structures. So segments tree with delayed operations are not guaranteed to work good in persistent case. I need to be careful with that. Okay, so let's see how amortized analysis is bad on persistent data structures and then make a short break. So yesterday, when we were discussing a problem of minimum in a queue, we have discussed that we can create a queue based on 2 stacks. Remember? Okay, so let's try to do the same and make persistent queue based on 2 stacks. I put 3 question marks there because it's doubtful that it would work, but maybe. Okay, so how would we do this? What's our plan? We have a queue separated here. We put our elements from this side, take elements from this side, and if it's empty here, then we ask those elements to walk around. So go away from this stack and come to this stack. They preserve the order that we need. What is the problem if we try to make this persistent? We already have the persistent stack, so if we make a persistent queue based on 2 persistent stacks, seems that we will have a persistent queue. We will, but amortized analysis breaks. How does it? Suppose you make 100,000 push operations. So now you have our persistent, so we have persistent queue that has all these nice 100,000 elements. Now let's make pop operations on this revision. What would happen? All of them would walk here. First problem is that we would create 100,000 revisions of our stacks in one operation. Well, but okay, we will make pop. It will go. But now, we have a persistent queue, remember? Let's go back to this persistent queue and make again a pop operation from it. To this revision, from this revision. Well, it's not very good because all these elements will walk here again. And not only will they work there, but they will also create again another 100,000 revisions of persistent stacks. And the first one will pop out. So if we have some amortized analysis, what is amortized analysis? We take all the operations and average them. There are different approaches to calculate what is the result, some coins, some potentials, or whatever. But the main idea is that you take a lot of operations and average them, so that on average it works fast. Slow operations are rare. But if you do this on persistent data structure, it doesn't work, because you can take that slow operation, even if there is one, as in this case, and make it happen again and again and again. So this way, amortized analysis breaks, because you cannot necessarily average that out, because you can make slow operation repeat again and again. It's not the case for segment street, because then each operation, it's not the amortized analysis, the delayed operations, we just redo them, so we lose in speed some constant value. But every operation is true logarithm, actually. We just don't make, those pushes are not reused if we start from that revision again. But again, okay, there is no amortization here, so it's okay to work with that. Just we have a plenty of, just when we make a read operation, we create the new version. It's not needed, maybe. And but if you read it, you still spend logarithm. So branch trees are safe. Another data structure that is not safe and that needs to be implemented carefully is a tree. What is the problem with tree? It's similar, although not exactly the same. There is no amortization in tree. There is randomization. Yeah, use random keys for priorities to make the tree structure random and avoid it getting a bamboo. But if you make merges of trees, of different revisions of the same tree, then randomization breaks, because there is nothing random. You have made this vertex with a random key initially, but then when you reuse it, it doesn't have a new random key every time. It has the one it got on its initial creation. So suppose you create a vertex, so it has X and Y. Well, let's make an implicit tree with no primary keys. So we just saw something like a rope, yes, like an array with link and cut operations and insertion to them. And so we have a tree with so it got some random key Y. Suppose you then merge this one and this one with itself. Okay, it would get something like that. Somebody would become somebody's child. Then if you merge these two once again, what would happen? So their keys are the same. So they would go to the same side as previously, to this side. That would merge to this. These keys are equal again. So that would go to the right side again, and that would become like this. All keys are the same. So if you merge to these ones again, you get also get a row of 8 and so on. So on this point we make a break and answer the phone. Please come back. Okay, let us continue. We have discussed not discussed, we have seen two problems. Let's start the second part of our class. We're talking how to solve these problems because we would like to have a persistent Q, we would like to have a persistent chip. There are actually two approaches how to solve these problems. One is a general approach based on what we had there on a segments tree implementation. Segments tree is very nice. It has no amortization. It has no randomization. It has no special cases. It is always logarithmic in depth. So making it persistent is perfectly safe. So what we're gonna do now, we're gonna make an array persistent using segments tree. So to do this, we just have an array stored in a segments tree with, well, when you have a segments tree, you usually have some operation on it, something like minimum or sum or whatever. Let's make no operation. So the internal vertices of our segment tree will have no meaning. They will only be used to make a logarithm speed access to a bottom level of our segments tree. And that bottom level will store the values of our array. So now we can access arrays in logarithm time. We can change values in our array in logarithm time, and we have a persistence because it works like this for segments tree. Therefore, we've made an array persistent with logarithm slowdown. And unfortunately, slowdown is not so bad, but the worst thing is logarithm memory overhead, but okay, that's what we are paying for that. And if we make this, we can take any data structure, whatever one we have, and make it persistent in one step. Just make it persistent by implementing it on the persistent array based on segment tree. That is an expensive but universal way to make data structures that have array-based implementations persistent. Okay? Now, but these two particular cases, Q and trip, have different solutions that are specific for them and don't give that logarithmic slowdown in case of a trip. They do give this the way I will describe does give a logarithmic slowdown on Q, but it also gives a nice idea, shows a nice idea that I want to share with you, so maybe you could use it in some other data structures as well. So let's start with the trip first. The problem with making tree persistent again is that if you would like to merge different revisions of the same tree, then it is possible and actually quite likely that they will have the same randomized key, so it doesn't become randomized anymore. And that leads to degradation of our trip to some longer, deeper trees like bamboo or something, and it removes our analysis that gives the access time based on randomness of this keys. So let's make an alternative implementation of a trip that doesn't use this randomized keys. It's called randomized binary search tree, RBST. What is a randomized binary search tree? What is the purpose of giving a vertex of a tree a random key? The purpose is to randomize the structure of the tree in the following way. The analysis is based on the fact that every node has equal chance to be the root of the tree. So, can we have another way to achieve that? The answer to this question is yes, we can. To do this, let's consider. If you recall the search in a tree operation, if we use one, or split operation, they don't use these random keys at all. They only are working based on either values in our tree that we store them, or on sizes of subtrees if we have index-based access to elements in our tree. So the only problem is with merge operation that takes two trees. So suppose you have merge operation on two trees of sizes m and n. Instead of using randomized keys, let us do the following. When we merge two trees of given sizes, let us do the following. Let's make a random number from 0 to m plus n minus 1. So m plus n possible variants. And then, if this number is from 0 to m minus 1, then the root of the first tree will become the root of the merged one. So it's A, B, yeah? So merge A right and B, and return A value, A left, and the new one. So it's new. And if this value from m to m plus n minus 1, then the root of the second tree becomes the root of the combined tree. So we get a new one as merge of A and B left, and return the one with B value new one and B right. So if we do like this, we have the following thing. Now we still have each vertex of the resulting tree has the same preliminary chance to become the root of the final tree. So this is by induction. So by induction, each vertex of this tree has equal chance to be the root of this tree. Each vertex of this tree has an equal chance to be the root of this tree. And then, so for the one from here, we have 1 divided by m times m divided by m plus n. 1 divided by m plus n chance to become the root of the new tree. And similarly here, 1 divided by n times n divided by m plus n is equal to 1 divided by m plus n. So every vertex in our resultant tree has equal chance to become the root, and we can use the same analysis we use for traditional trees in this implementation. And it doesn't suffer the problem that we have discussed, that equal key auxiliary keys result in degradation of the trip to a line. Because now every time we merge, we reroll our random. And it goes independent in all. In persistence, we have different storylines. Yeah? So in every storyline, we have a separate analysis of this randomness, and it gives us an explicit probability of 1 divided by m10 plus n, 1 divided by the size of the tree, for each vertex to become a root. So our axis time averages and all the other things all are as in normal trip analysis. What I'm saying is actually not absolutely mathematically true, because we have the simpler thing, the probability, yes, but the other things related to distributions maybe are not exactly okay, but in general it works fine. So the absolutely strict mathematical analysis is not what I'm going to do here, but I think that the idea is okay. So you can do persistently, confluently persistent trips using this idea. Any questions on this? Okay, then let's go to persistent queue. There is actually a way, if you really want to know a really weird thing, you can try to Google for queue real-time queue on 5 persistent stacks. I will not tell it now, but you can Google for it if you wish. It's very interesting to read. So they remove amortization from this algorithm, so they implement the queue on 2 steps, but they remove amortization. To do this, we need 3 additional steps for a total of 5. Actually, only one of them is persistent and non-persistent implementation of a queue, but all of them are persistent if you want persistent queue. And this gives real time or constant time queue, but that's nice, but that's weird. But what I will talk about is nice and useful, I think so. Although it gives logarithm slowdown, unlike that thing. The thing I'm going to talk about now is how to make a persistent queue without any stacks, but on a very interesting structure of exponential tree. It is sometimes called an exponential tree. Let's see. We will not only make a queue, actually, we will make a deck queue. Double-ended queue. We will be able to push and pop from both sides. Well, okay. So what we're gonna do? We're gonna have a tree that has the following structure. Every node has front buffer of size 1, tail buffer of size 1. This size can actually be varied in a time-memory trade-off. We can make these buffers larger to lose some memory and increase the basis of logarithms, therefore getting faster access. And a child tree, child node, that has the same structure but on pairs of elements. So you cannot write it in C++, but if you tried but if you try it, it would look something like that. So node of T is T has T front, T tail, and a node of pair of TT child. So unfortunately it doesn't work because C++ compiler, at least in C++ 14, I don't know, maybe they increased the power and new revisions, tried to expand this, and then this, and then this, and went to infinite recursion and couldn't compile this. But the idea is like this. So let us see how it works. The child is also, it's not a node, of course, it's a reference, yeah? So it's a pointer, so it can be empty. Also, both of these can be empty, so maybe we could use something like this. So, let's see. I will describe push and pop from one side, push and pop from the other side asymmetric in a sense that front and tail correspond to each other. So how does this work? Suppose you make push from this side. If front element is empty, then you just put it here and you have a front element. So let's try. We begin with an empty. Let's see another example. So we begin with the empty ones. It has no child, no front, and no. So we push to the front and say the number 1, and if it's empty, just occupy this place. If front is not empty, so for example, say we want to push 2 here, then we take the current front element and the one that we want to push, create a pair of them, and push it to our child. If it doesn't exist, we create it. So in a persistent way, we of course do not change any values. We create the new nodes. If we don't have, if it's not persistent, it's unclear why we do this. But if we do, we can just change it. So if we push 2 here, so that becomes empty, and to tail is still empty, and to the child we push the value of 1, 2, or 2, 1, yeah, the pair. So and so on. So now if we push 3 here, its front is still empty, so we would put it to the front. If we push something else here again, then, okay, it's not empty, so we create a pair and push it down. Here it is not empty also, so we create a pair of pairs now and push it down. Of course, if we don't want to copy all these things, so we use pointers actually everywhere. So like this. So it goes down and down and down. How far down can it go? If we have, I call it an exponential tree, because every value on some level, on a level d, stores 2 to the power of d elements of the original type. So you can go down at most logarithm of the number of elements in your structure depth. Okay? Now how do we pop from this? In a similar way, although there is some small trick. When you pop and the buffer at the side that you want to pop from is not empty, you just take the value from there, and it's okay, it's your popped value. If you want to pop and the buffer is empty, for example, we want to pop from here, we look at our child. If we have a child, your implementation must keep track of empty subtrees and remove them, because if you don't, this would break a little bit, although not very difficult to fix anyway. So if we don't have a child, then let's look at the buffer on the other side. If it's not empty, then return the thing. If it's also empty, then we are empty at all, so nothing to pop. If the buffer on our side is empty, but we have a child, then recursively pop from a child. So in this case, this buffer is still, we want to pop from a child here, and this buffer is empty. So we must pop from our child. We try. In a child, this buffer is empty, we have no child, but we have buffer on the other side. So we do this. We return, we have popped to one pair from our child, and our child is empty now, so we erase it actually. In a new edition of this node, we will have an empty child. Now, we have popped a pair actually from our child. Well, okay, we split this pair to two elements. The second one, actually the first one, if we pop from the child, goes to the buffer, and the other one is returned out, which is popped. So that's how it works. If you push, if the buffer is empty, you put it down. If the buffer is not empty, you create a pair from the thing in the buffer and what you want to push, and push it down to your child. If you want to pop, if the buffer is not empty, you pop that. If the buffer is empty and the child is not empty, you pop from the child. Split the pair you pop to two parts. One part goes to the buffer, the other part is popped. And finally, if the child is also empty, you check the buffer on the other side and pop it if possible. So that's it. That's a nice exponential tree implementation of double-ended queue. That has a logarithm. That is a logarithm depth tree, so it can be made persistent using standard technique similar to range, two segments tree or Cartesian tree, just to create a new node instead of modifying values every time you change them. Okay, any questions on that? No questions. Okay. Any comments? Okay. Pop parts. Repeating the pop parts. You see. Okay. Let's write down. So you see, you have a node. You have the buffer, the child, and the buffer. The child. You are popping from one side, any side you can pop. For example, from child side. So variant number one, tail is not empty. Tail is not null. Then we just return the tail value, and tail becomes null. It's okay. Now, second variant, if tail is empty, then check your child. If child is not empty, then we pop from the child. So we have a pair AB popped from the child. So why do we pop a pair? Because child contains pairs. So this pair, A, the first element, goes to the buffer, tail sent to A, and B is returned. So we keep order of our elements. They were the order of elements is the following actually: our front, child's front, child's front, and so on. Inside this, there are complex structures. Some we can say trees, yeah, inside of these, and they are from left to right. So the order of elements in them is from left to right. Then finally, the bottommost child is tail, previous child, tail, and our child. So that's the order of elements. So when we popped something from the child, that were the tailmost element of our child. So A was previous to tail element of our whole structure, and B was the tail element. So we return B, and A is now the tailmost element that goes to our tail. So the third variant is when our child is also empty. So everything is empty. Tail empty, child empty. Then the only candidate to be returned is our front, because there are no more elements. We have a single element, and it's stored in a front buffer. Third variant, tail is null and child is null. So if front is not null, we return front and set it to null. And if front is also null, well, we are empty. And something bad happens. Whatever happens when you pop from an empty structure, nothing good can happen. Okay, anybody else wants some details on that? Well, okay, then I have an exercise for you with no report, so you just solve it and enjoy. Make this structure cacheable. Devise an algorithm to concatenate such structures. So you have two exponential trees, and you want like merge in Cartesian tree, like merge and tree. So merge two such trees. Try to do this. It's a nice exercise. It's not very difficult. Okay, any more questions or comments? No? Okay, let's move on then. Okay, I think that's it for persistent data structures. I want to tell you some more things without a particular connection to each other. Without a particular connection to each other. Just few more stories about data structures that you might know or you might not know, but that are in some sense useful. Okay, so the story number one will be called story number one. It will be called Sparse Table and a Friend. So most of you, I guess, know sparse table data structure. I will now quickly refresh it. But not all of you, I think, know that sparse table has a friend. That sparse table has a feature, well, not a feature, a requirement, that for overlapping segments, the result must be okay anyway. Actually, this requirement can be removed with its friend. So we'll see now. Okay, so let's go. What is a sparse table? A sparse table has the following structure. Suppose you have some operation, for example, minimum. Let's see. Let's make a single element segments. Then let's make two element segments. But unlike segments tree, we will not make non-overlapped two element segments, but we will consider all two element segments. So this one, this one, this one, this one, this one. So all two elements. Then again, all four element segments. So this one. Then we need four levels to draw them clearly. This one, this one, this one. So they are overlapping, and so on. Now 8 element segments and so on. So for every segment, we will calculate the value of our operation, say minimum, for this segment. And that is our sparse table. So sparse table ij is minimum among our values. Let's say we have an array called A, for example. Minimum among aj plus 1, and so on, aj plus 2 to the power of I minus 1. So sparse table is easily initialized with various. So sparse table 0, j is just aj, of course. Well, minimum again here is just an example. You don't absolutely need minimum, but there is some requirement for this operation that we will now see. And for greater values of I, we have a recurrence, so something like sparse table for ij, for I plus 1j, let's say, is minimum. So we take this segment of length 2 to the power of I plus 1 and divide it into two parts of length 2 to the power of I. Minimum of sparse table ij and sparse table ij plus 2 to the power of I. Or 2 to the power of I is easily constructed as 1 shifted by I. So sparse table allows us to quickly answer to the question of the minimum of whatever operation we build it for on a segment of length 2 to the power of 2, but also on any other segment in the following, with the following trick. You see, you have a segment from L to R, and you cover it with 2 power of 2 segments like this and that. So they are both of the same length, and they can intersect. But for our particular operation minimum, it's okay. So we have a requirement for our operation. It must be so-called idempotent. That means that if we denote our operation as a small circle A must be equal to A. So minimum is okay. For example, greatest common divisor is okay. Or for Boolean values is okay. Some other operations like plus or multiplication are not okay. Can we get rid of this requirement for the operation to be idempotent and still answer in constant time to any segment queries? The answer is yes, and we have a similar structure to the sparse table that stores just different values. Okay, so let's see. Take your array. Let's this length be the power of 2 for simplicity. It's actually not very much needed, but it's easier to explain it this way. So 0 to the power of k. And divide it into 2 parts in the middle. Let's calculate values for every... let's do it for the operation plus as an example. Although for plus, of course, it's much easier because plus has minus. When the operation has minus, the inverse, you can easily count it on segments by making it prefix and subtract this prefix. But if we will not use minus, so it will work for any other operation. I take plus to make explicit that we don't use idempotent, because plus is clearly not idempotent. If you wish, you can take matrix multiplication as an example in your head. It is not idempotent, it has no inverse. Some matrices are degenerate and they have no inverses, yeah? Okay. So check the middle of our segment, or of our array, and for every value to the right of the middle, calculate the prefix sum from the middle to this value. So this value, this value, this value, this value, prefix sums. For every value on the left of the middle of the segment, calculate suffix sums to the middle. So like this, 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 and so on. Now let's take some array and let's take some segments, sorry, and calculate the sum on this segment. So we have a segment, and clearly the sum on this segment is this suffix sum plus this prefix sum. Okay, you tell me that that's not true, not working, because what if the segment is completely to the left or completely to the right? That wouldn't work then. Well, okay, that wouldn't work, but we still haven't used our logarithm. The sparse table has logarithm and logarithm size, and we only have linear size yet. Let's recurse to the left and to the right. So for values to the left of the middle of our segment, do the same. Take the middle of that segment and find prefix sums for the right part and suffix sums for the left part. But now we will not go beyond this middle point of the previous level, only inside this left part. Similarly, we will take the middle of the right part and do the same thing. Okay, so now if the segment is to the left or to the right of the middle point, we don't use the first level, but try to use the second level. So if the second level is like this, then we need to go to the left, to the right, and sum them up. Of course, this can be again the case that it is in one half, so we must go there. So the first thing, our new friend of the sparse table. Let me introduce it to you. I don't know, this structure has no common name that I know. Probably it has, but I don't know. So I call it a friend of a sparse table, but you can call it as you like, or maybe you can find me the real name of this and tell me that I will use it. I will use the correct name. So our friend is for level I. and the value j is, it's not so simple to define. The idea is that we check. So let's not use here j, but so we check. Let's number the levels in the other direction. So this will be the topmost level. It will be level number k minus 1, and the bottommost level will be number 0. So if we take s times 2 to the power of I plus j, where j is from something like minus 2 to the power of I to the power of I minus 1, or not minus 1. Just like integer number representation, negatives have more power here by 1. Is the sum from okay, now let's make positive and negative separately. So if j from 0 to 2 to the power of I minus 1, that's sum for t from s to the power of I to s to the power of I plus j of a t. And if j is from minus 2 to the power of I to minus 1, then it's sum for t from s to the power of 2 to the power of I plus j to s times 2 to the power of I minus 1 a of t. So that's, I think that we need two formulas. And how to find the answer for the segment? We have L and we have R. We want to find what is between them. What is the power of 2 between them? How to find one? So let's see. The answer is we must find the topmost bit in their representation that is different. That is exactly the power of 2 that is between them, because for all other powers of 2, greater powers of 2, 0 means they are both to the left of it, 1 means they're both to the right of it. And for this power of 2, that bit in their binary representation is different, for that power of 2, they're on the different sides of it. Okay, get it? So we take binary representation of L and R. We find the topmost bit that is different, of course, because L is smaller than R. L must have 0 and R must have 1. Here they are equal. And for that level, now we refer to that level of our Fresnel's sparse channel. So how to find this bit? We might take L XOR R, XOR exclusive or R, and get the topmost bit. Similarly to a sparse table, we can pre-calculate the topmost bit for all values. It's absolutely the same code that sparse table has. So we take the topmost bit of that is our level. That is our level. And then we must just ask for R on that level and for L on that level. The values are already created. This is filled already in such a way that they contain the correct value that you need to refer to. don't need to make any other bit operations. So the array already contains what you need to sum. You just need to pick the correct level, and the correct level is this. Okay, so that's it. Do you like the friend on the sparse table? It allows you to have any associative. I think commutativity is not necessary, although without it, it would be a little bit more cumbersome to calculate all these values. But I think commutativity is not necessary. I'm sure commutativity is not necessary. So for any associative operation with n logarithm n time pre-calc and n logarithm n memory, you get constant time segment request. No inverse and no idempotence needed. Yes?
Explain in more details, please. What is this that S that's multiplying?
Well, you see, on this level, take a look. On this level, you only have 1 times 2 to the power of k minus 1. It's level k minus 1. On this level, the middles that you use are 1 times 2 to the power of k minus 2, and 3 times 2 to the k minus 2. And between them, you calculate these prefixes and suffixes. So S is this 1 or 3. On the next level, you will have 1, 3, 5, and 7. So here S is odd. So that's just the formula. I don't write an explicit code, but I think you can do it, getting what you have to say. Other questions? Well, okay, what is the time now? Okay, let's make another but now very short break. Don't go so very far. Please come back soon, because I have 2 more stories for today. our stories today. And the second story for today will be, well, it's not the second story, it's the second of these stories, yes? So we had many stories actually. Okay, the second story for today will be segment tree of sorted segments and fractional cascading. Fractional cascading. It is also sometimes called a merge sort tree. So suppose you have some requests for some queries, and you want to have all the numbers, and to answer these queries you want to have an array as usually. To answer your queries you want to have all the numbers of some segment in sorted order. Well, it's not easy to do this. So, okay, you relax your requirements and say, okay, I agree to have all numbers in the segments as a collection of its subsegments, but all of them are in sorted order. So this way you can process some queries on them with something like the number, to count the values that are greater than some number by using a couple of binary searches or something else. So, what would you do? There is a nice data structure, segment tree of sorted segments, or merge sort tree, that can help you. Let's build it. So, let's take some array, say 3, 1, 4, 2, 5. I don't remember them, so we make other numbers, 1, 7, 6, something like that. So let's make this will be our bottommost level, and for next levels we will do the following. We will make kind of segment tree, but we will not take some minimum or sum or something, but we will merge two segments in children to get a segment that contains all the values from the children. So that would be 1, 3, that would be 2, 4, for example, 1, 5, 6, 7. Then we go to the next level, and we have like 1, 2, 3, 4, 1, 5, 6, 7, 6. So nice here, and here we have 1, 1, 2, 3, 4, 5, 6. So that is called, that is sometimes called a merge sort tree. So if you want to have to process some segment in it, like this, you can take a couple of segments that constitute to that segment. So you will always have a logarithmic time of segments, and all of them are sorted. So you can make some queries on them. But the thing that we will now do is that we will modify the structure a little bit to allow for a simultaneous search in all these segments. So, for example, consider the following problem. You want to know, to answer for a segment, the number of elements less or equal to some value. So how would you do this? For example, less or equal than 3 for this segment. These are values 2 and 1. How you do this? You take all segments and make a binary search for each of them. So for example, here you make a binary search and see that it's 2. And here you make a binary search and see that it's 1. And here you make a binary search and see that there are none. So the total number is 2. The thing is that we can add additional information to this tree that allows us to avoid these binary searches in similar queries. This is called fractional cascading. I don't know why, but it is. Let's get back to the process of us building this structure. How do you build a segment actually? When you build a segment, you do the following. You take your children and run a merge from merge sort algorithm for them. So you see what is the smallest one. 1 or 2? 1. So 1 goes here and we move pointer to this position. What is the smallest of 3 and 2? 2. So 2 goes here, pointer moves. What is the smallest of 3 and 4? 3. 3 goes here, pointer moves. What is smallest of the end of the segment? And 4. 4, so 4 goes. So that's how you do it. When we do this, let's do the following. For every number that we put to the segment, let's put 2 pointers to the left and to the right segment to the position of the pointers where they were at when we move this number to the top. So in the pointer, in the segment that this number came from, that would lead to this number again. And in the segment, in the other one, that would lead to the position where this number would be inserted should it be in that segment. Okay? So here, for example, we compare 3 and 1. 1 goes here, so 1 is pointed here, and 1 is pointed here in this segment. Now, 3 and 1. 3 is again pointed here because before this 3 went out, and here we point after 1 because 3, when we copied 3 here, we were after this element 1 in this part. So similarly here, for 2, we both were here, and for 4, how I draw it? And for 4, we were before 4 this, and after 2 here. So similarly on, so here 1, 2, 3, 4. 1 comes out, so we are before 1, and here we are before 2. When 2 comes, here we are after 1, here we are still before 2. When 3 goes here, here we are before 3, here we are after 2, and so on. So actually, I draw this as arrows on a board, but in your program you just store the indices of this merge operation into additional arrays for each level. So finally for the 4, that will go like this. Why is it useful? If you have this structure, you can avoid binary search in each array, but you can look for the value of in each array that you approach in your segment tree. You can always know the position of any value without binary search. So for example, when you want 3 in these 3 arrays, you start from the root node. So you see, you are here, and you have a reference that you were here and here when this 3 came. So here is the 3, and here is the position where 3 would be in this area. So when you descend to this area, you know that this is the position where 3 would be in this area. And when you descend here, you know that this is the position and this is the position. And so here again this, and here again So if we had binary search in each of these areas, then it would take us logarithm n for binary search times logarithm n for each segment, or for the number of segments. And if we use fractional cascading, we have a constant memory expansion because we need to store these pointers. But we have only one logarithm for descending. If we need to find the number, we can always find the initial position to start our descending in the root area with one binary search, not in every segment. So that's a short but useful story to remove one logarithm in some process, in some tasks when you have to work with that merge tree. Any questions on this? Okay, then we have some 5 minutes, and that's perfect to tell you about a funny data structure for the end of today's lecture. It is quite funny. It's not that very useful as the previous two ones, but it shows you some nice feature. It's called 1 and the boss tree. Have anybody heard about it? Yeah, no? Okay. So this is the not that it was very tree. This is a data structure that allows us to work as some kind of tree, some kind of heap. So it allows us, but actually even more. So it allows us to do almost like, it takes approximately a set structure in C++, but it has alternative running time. Or if you store values from 0 to 2 to the power of n minus 1, it answers equations in time logarithm n. So it's a logarithm of max value. Unfortunately, it's constant. It's not that good. We have tried, my students tried to implement that. It is about 3 to 5 times faster than set. So it's not very useful at contests, I think. But again, it has some ideas of advanced data structures that can be used. Maybe parts of them can be used in actual problems. But what is a 1M boss tree? 1M boss tree is again similarly to exponential tree. It is a recursive structure, so it is parameterized by the number of bits in the number it stores. So let's investigate how 1M boss tree of n is organized. So we will look at it as a set structure. So we can add elements to it, remove elements from it, find minimum, and answer queries, lower bound type queries. So find the first value greater or equal to the given one. So it completely encapsulates set function. What it has? I will use, although it's not in our language actually, I will use notation int of n, so that we have int with n bits. Just to explicitly show how it works. Okay, so first of all, let's go and talk about one and the bonus of 1. Well, it's just 1 bit value, so it's 0 or 1. We will implement it as an array of 2 elements, 0 and 1 of Boolean. So if we are just, do we have 0 or do we have 1? So the bottommost level is just a special case. So for n greater than 1, let n be the power of 2. It is actually the case for integer values in common computer architectures, because in 32-bit you have 32 is a power of 2, yeah? And 64-bit now you have 64 as a power of 2 also. So the number of bits is usually a power of 2. So okay, if it's not, surprisingly, if we will have some weird architecture that have no power of 2 number of bits, that would be very strange, but we would have to expand it, or we cannot use it. So we separately store the minimum value. It's in something similar to the exponential tree. And we also store 2 additional arrays. Actually, in real life, you would not store them as explicit arrays because that would be too memory heavy. But you would use maybe some hash tables, and that would slow it down again even more. Maybe at the topmost levels where you have many bits, you would use hash tables, and at lower levels, when you use few bits, you would use arrays. So we have an array of length, not an array, we have a 1 and the boss tree of the size 2 of one smaller power of 2 of, we call it ups, not because of oops, but because upper parts. So. And we have an array of 1 and the bonus trees, 2 to the power of k minus 1 downs or lows of length 2 to the power of k minus 1. So again, we separately store our minimum value, and we separately we store 2 and bonus trees. This one contains, let's take an n-bit integer. It contains of 2 parts, so it has n bits, n divided by 2, and n divided by 2. N is 2 to the power of k, so n divided by 2 is 2 to the power of k minus 1. So this is we call upper part, and this is we call a lower part. So we have some integers there. The minimum value in the whole tree is stored in a separate, absolutely separate value here. It is not stored in this part, so it is exclusive. It lives here. For all the other values in the tree, we have upper and lower parts. Upper and lower parts. Upper parts live in a special 1 and the boss tree, and lower parts live in the array indexed by the upper part, and for every upper part we store which lower parts are there with this upper part. So that's how it looks. Weird. And this array, as I have told you, it's very it's very expensive, so you would, at upper levels of the tree, you wouldn't use an array, you would use some hash table or something for that, because if you store only a few values, it would be very empty, so it would have very few non-null elements. So let's see how we work with that. So actually the structure is the most important thing. The structure imposes the usage. So what we do, we want to add some number. Let's talk about insert first. The first thing we do when we make an insert, we compare it. Well, if we are inserting into the empty tree, that's very easy. We put it as a minimum value. All these are empty and we are done. So this is constant time. If we are inserting to a non-empty tree, the first thing we do, we compare it to the minimum value, and if the minimum is greater, then our new insert value is minimum, and we insert our old minimum. So we just swap them. So we always insert to this part. Is this part clear? If we want to insert the value that is less than our current minimum, we put it here, and this minimum is just what we need to insert. So now, the next thing to do is to insert into these two parts. We first need to insert into ups, our new upper part. To do this, we first want to see if if we actually have such upper parts. So we need, if we don't have let our insert return something like a return. Was it actually inserted or was it already there? So no, not like this. So first thing is we want to see if we have at least one number with such upper part. To do this, we take a look at our lower parts, if this tree exists or not. If this tree exists, so we have this tree in this area. So let's see, it's up and low. So if lows of low is not null, so if there exists a tree, then we already have the upper part, so we don't need to insert into the ups. And we only insert into the lows. So lows of up, lows of up, insert low. In the other case, if it's null, then we must insert the upper part. So we make ups insert up, and low ups, low of up is new tree, and the low of up we insert lows. So that's approximately how insert goes. So it checks first if there is at least one such upper part by checking that this is a non-empty tree. If this is a non-empty tree, then we just insert it there, and if it is empty, then we need a new up, so we insert it into ups, and then we insert it into lows. But the trick is that actually, in this case, this insertion is very fast, because this was an empty tree, and so we just put it to minimum, so it's constant time. And in both cases, we have only one recursive call to a tree that has twice shorter ins. So in logarithm, the depth is only logarithmic. Okay, let's see how to find, say, lower bound. To find the lower bound, what we need to do is to find the value that is greater or equal to the requested value. Again, have a requested value up and low parts. So if the requested value is less or equal to minimum, then okay, we have minimum as the answer. In the other case, let's see. Let's take our three laws of up again. If laws of up is not null, laws of up is not null, then okay, let's try and see if we have now let me check one thing. Let me think a bit. So then we want to find the I think that we need also to store the max value here. Let me make a small correction to what we saw. We also saw additionally a maximum value in our tree, but we don't, unlike minimum value that is stored separately and is not stored in this recursive structure. Max value is stored there also. It's only additionally stored, so you only keep track of it. So when you make insert, you also check if you are exceeding current max. So if it's not, we compare it our low with maximum value in that subtree. So if it's less or equal, then we make a recursive call, return high times 2 to the power of k minus 1 plus lows of up, lower bound of low. And in the other case, if laws of up is null, or if laws of up maximum value is less than low, then we need find minimum value that has strictly greater upper part. And among those, the minimum one. So in the other case, we make up from up lower bound of up plus 1, and that returned value, we go to lows of that value dot min. That's the result. That's always the result. We don't need to make any other upper bound or lower bound calls there because we already have strictly greater upper pass. So lower part must be minimum pass. So again, we have only one recursive call. Well, and finally, what we would do to make to remove. We make a remove, I answer questions, and we go to lunch, okay? Other things like minimum, maximum are stored explicitly. Insert we have made, lower bound we have made. Again, the main idea, you see? The main idea is to never make two recursive calls to both ups tree and one of the lows tree. So we investigate first which of the recursive calls to make, and then make only one. And the common idea that I want to present to you in this data structure is that it is actually this. So when you make some interesting data structure, sometimes explicitly extracting some minimum value or maximum value in it can let you do this, can let you avoid doing some recursive stuff. And that, well, in this case, it's quite weird. It allows you to save in the set of logarithm and you get logarithm of size. But in some other cases, it may turn you to logarithm instead of linear, or logarithm instead of logarithm squared or something. Yes, the question. Well, we have, not high, sorry, up, yeah? Up. So we know that our up part is the same in the result, so we keep it, and lower part we use recursive. Okay, let's remove now. Remove. I believe remove needs remove min. Let's first make remove min. Okay, how remove min works? Remove min works in the following way. We want to remove min. To remove this minimum value, we need to find the minimum value in that part, remove it from there. Let's discuss. So let's look at the mean value in ups. That's constant time because mean is stored explicitly. Let's now look at this lows in this with this index. Its mean is stored there explicitly also. So we know the new minimum value. Now the only part is to remove it. And here is a usual trick of this structure. If lowest part with it up with the minimal upper part has only one element, then removing it takes constant time. We remove it and are left with empty tree. We see that it is an empty because this ups tree is empty. It has no minimum. It takes constant time, and then we remove this minimum from ups. And if we remove minimum from the corresponding lowest parts, and it is left non-empty, then we don't touch ups because we have lower with the same upper part still. So remove min goes like this. Remove min goes like this. If new min is ups min times 2 to the k times 2 to the power of k minus 1 plus lows from ups min dot min. So this is constant time. Now we lows with ups min, remove min, and if it becomes empty, it's null. So it's not exactly what you would write in C++. Remove min, we cannot get this null, force this to become null. So you need an external function for this. But I will write it like this. So you go and ups remove min. If this requires 2 recursive calls, then that would mean that this call was in constant time because it removed the only element min and made no recursion. And remove now is similar to remove min. So we see if we need to remove minimum element, we remove min. In the other case, we don't touch min. And see on the upper and lower part. If we first check to remove the lower part, and if we are left with empty, we remove the upper part. And again, to be left with empty, we need to have constant time removal of the only element. So that's it. How do you say now? Creepy. Okay, let's summarize what we had today. We had some useful things, had some less useful things. From among useful things, we discussed two-set problem. I hope you will always solve it correctly now. Implications to segments using prefixes or suffixes and using segment tree. Then we discussed persistence. Oh my god, we have forgotten a very important thing. Now we have to 5 minutes delay our lunch. But we have to talk about this. I have promised you and I have forgotten. I'm sorry. That is very bad. Let us finish the summarization and one more story. So one more story, but very important for contests. Then we had several, and in persistence we had Q and Q using exponential trees, any array using segment trees, randomized binary search trees instead of trees to get rid of problems with equal randoms. Yeah, and then we had 3 stories. Sparse table and friends, and a friend. We had fractional cascading in merge or tree, and we had a very strange data structure, one named the boss tree. And now we get back to persistence, because I promised you 3 days already to tell you how to solve online problems in the offline if you know how to solve them in the offline setting. So let's do it on the example of the problem L of the first day. But the technique is general, I think you will clearly see it. So you have some try, and you add strings one by one, and you make queries of the sum to RSQ structure. You make queries of for elements from L to R, the sum of elements from L to R, and you make changes. When you add the new string, you rewrite it with the new number. So you make changes to that segment tree values, you decrease by 1 the old value, and in the end you add the number of newly updated vertices to the corresponding sum. So what you could do, you could sort your queries by the right end of the query and do them in this order. Then you interleave answering queries with this R value, enter in the next string, answering queries with this R value, enter in the next string, and so on. You do this, then do that, do that, then do that. Okay, let's do the same thing, but without knowing queries. We just imaginarily answer queries, add the new string. Answer queries, add the new string. So, how could we answer these queries afterwards if we didn't know the queries before we answered some in future? Okay, let's not answer them, but let's use persistent segment string instead of an original one. So when you do the following. You add a new string, store the current state of your segment tree. Add a new string, store the current state of your segment tree. Add, store, add, store. So, how do you store this? If you are using persistent segment string, you just store the reference, the pointer to the current root of the string. If you remember the picture we had, after you make a modification, the new version behaves completely as a solid segment string which doesn't know anything about other versions. So, after you're doing so, you have queries. So you have query with some value of R. What would you do in the offline setting? You would answer it somewhere here. Okay, we have a special thing. We have a stored version of a segment tree that was between this and this string. So we use this particular version of a segment tree to answer this query. We get the answer, we know the new L and R values. Okay, let's see. This version, for example, or this version will be used for the next query. So this is absolutely a general technique. You suppose you have a problem in the offline setting, so you know all queries. You sort them by whatever you like, imaginarily, and run your solutions. But instead of answering queries in any place of your program where you would answer them, you instead store the current state of your data structure, whatever one you use, using the persistent one. After that, you get your queries in the online setting, and whenever you have some query, you just take the version that you need to answer this particular query and answer it. So you conserve you store the intermediate versions, and you have access to them for later answer your queries. Okay? Okay. So thank you for listening today, and as I know tomorrow you have a sponsor day, so I will see you today at the contest, I think, and tomorrow we have no lecture. If you are after done with sponsor activities, you can have a rest, or you can have absolvent, or if you need my help, you actually, yesterday there were requests how to contact me. You can write me an email. Let me write down my email address. Or you can write me on Telegram. So, if you wish, if you have some questions, I don't promise that I will answer just in a few seconds, but I will try to answer you if you have some questions while absolving. But please don't send me requests, send me test number 45. I don't answer such requests. Okay, so that's it. Have a good lunch and see you on Contest today and on Friday. Our theory continues on Friday.